exploring. So yeah, without further ado, let's jump into it. But, you know, obligatory GIF first. So, who am I? Trevor Clarke. I've done software for a really long time now. I've been making things forever, since I was really little. Like my first stuff has just been always building, like since I was 2, basically. Back in high school is when I learned about a program called First. I don't know if you guys have heard of that before. Dean came in and made the segue. Had a program called First where you could, in high school, get exposed to robotics and things like that. And the year that he invented the Segway, I immediately wanted to build one myself, and I did. That took, again, the same level of experimentation and breaking things until me and another guy, I built the chassis and he programmed it, and we just built the Segway. So that, and many years later, experimenting with 3D printing, when that first came out around maybe 2009, or not when it came out, but like when other common folk like me could do 3D printing, that's when I started doing that. So you'll see a part of that in a little bit. And sometimes I throw in dad jokes. We'll see. Cool. So, a couple of you guys have mentioned this already, but I just wanted to get a feel for where everybody was at. I know I dabble in robotics. I'm by no means professional. But yeah, how many have actually built robotic things? Cool. And how many of you guys have never even heard of a stepper motor? Awesome. So I'm going to talk through mostly how to get a stepper motor running, so you should be able to do it on your own with an ESP8266 or anything else, really. This is the logic side and the hookup side. And how many of you guys like GIFs? Awesome. So, I like to narrate things with GIFs. Anyway. So, the first question I want to answer is, why JavaScript? Like, I could really do Python or C or any other language. I'm doing JavaScript because I like it. There's a few other reasons. One of them is it can be asynchronous. In my adventures so far, I've found that I can do a few things asynchronous, other things I can't. Like, there's an example in here, there's only single thread execution. I want to somehow get around that. We'll see. Another thing is it has events. There's a couple code examples in here that have events running. I plan to do a lot more with that, especially with maybe human interaction. If something goes wrong, that can throw an event and cause the loop to pause or something of that nature, which you don't see happening in things like current 3D printers or other robotics. And the other thing is it's kind of developer friendly, because I feel like there's a lot more developers now doing JavaScript that have knowledge they can apply towards making things run. Like what Joel's doing here, he knows JavaScript. He's able to connect these physical things to the world with JavaScript. So a couple challenges. There's not many modules written. There's single thread execution, hard to find. SBC, SOM. SBC meaning single board computer or system on module. The modules that I'm talking about are things that run like a stepper motor. What is the code that can run a stepper motor? There's things like, many of you guys have heard of Johnny 5 possibly, and that runs on the actual computer. It doesn't have very detailed modules written in JavaScript for if you want to control a 6-axis robot arm, for example. There's not a coordinated way of doing that yet. SBCs, SOMs, those I'm still on the look for. If anybody has suggestions, I'm super open to it. I've looked through probably 60 boards now, and I'm looking specifically for a runtime for JavaScript with specific GPIOs and things like that. But if you're interested in helping me in that way, talk to me later. Next one, why not Johnny 5? And I just want to expand on that because it's very lengthy. You have to have, the biggest reason is you have to run it from a computer. I want to be able to have this thing clonable so I can make multiples of these and have them work together on their own. Like, you give it a set of instructions, it executes the instructions, and maybe it can collaborate with a couple at the same time. We'll see. The next one is the modules are very sparse, they're very basic. From what I've seen, you could get up and running with things like switching on and off lights. You could do the shades, for example, with stepper motors. You could have those go down and up, but there's no way to control multiples and coordinate them. And then again, sensor feedback is limited as well. So it's the same all around, everything's pretty basic level. With that said, let's start talking about the cool parts. So what I want to go through first is the control loop. In robotics, there's a concept of you've got a device and you want to do something with that, but you want to know, like, if it's in this position or if it's in this position or this position, and you don't want to guess. Like, if you wanted to do something useful, you don't just want to have it like you give it 200 steps and you hope that it gets there, and if it doesn't, if somebody gets in the way or power failure, then you may have just you have to redo whatever you were trying to accomplish entirely. So with that, a control loop is what I want to talk about in a moment. Cool. So the first thing that we need to do in this recipe, and it'll kind of build on itself, is a control loop. And with that, you have some way of calculating, well, you have something you want to do, and in this case it's a motor, and that motor spins. And then you have something that reads where that is actually in real space. And a PID controller, that's what the technical people call it, which is a way of giving a set of instructions to this motor and making sure that it actually gets there and does that thing. So you say, I want to go 200 steps. You send 200 steps. In reality, the forces that act against it make it go 197, and you say, okay, I'm 1 degree off. And in my level of precision that I want that 1 degree to actually happen. So it says, okay, I read that it's 1 degree off, calculate the steps to get back to 200. And that's where we can get the next level of accuracy from this machine. And that's what I'm looking for. So the control loop, again, is just a way of measuring what's happening in real life and making sure that happens. So this is what it looks like. You have an MCU, in this case JavaScript, and in my example, you can come up and look whenever you feel like it. It's a little tiny board called an Espruino Pico, and that's got a JavaScript runtime exactly like your ESP8266. I'm using that mostly for demo purposes until I find a board that I'm happy with. The next part is a motor controller, and in this example here, there's 3 of them. I'm going to run 3 different motors tonight. This controls the power output to the motor. So when you send a specific pulse to that motor controller, it handles all of the actual electrical current the way that it needs to for that motor to run. And that's really critical in stepper motors, which I'll get into in a second. And then alternatively, you can see it, right? Yeah, you can see it here. There's a sensor that sits separately from the motor. So it can either be right alongside the motor, in line with the shaft of the motor, or it can be wherever the axis of rotation is. In this little demo here, hopefully you can see it, there's a stepper motor right here, and then there's an axis of rotation over here. And I actually have a sensor reading on the axis of rotation and not on the motor. So that way you can kind of see the difference between having it on the motor versus off. It's going to know what the precision is out here and not what that, like, if I remove the belt, I wouldn't know where the other thing was. So that's an example of having the sensor where you need it. The other part of this, and this is kind of the same thing as a control loop, just a different way of thinking about it, is a closed loop, which means this system right here is contained. The feedback that I'm getting from the sensor tells me precisely where the axis of rotation is. Anything outside of it, I don't care, but inside of it, it's a closed loop system. I know what is going to happen. And the recipe for that is an actuator, a motor, a system of dynamic change with a sensor, some logic that is the PID controller, which helps that loop actually function. And then another thing that I like to think about is a defined range of motion. In this robotic arm, it can't go a full 360 in many cases. In this case, the wires would get tangled internally. In this case, it would start to hit if I had something on the end of this. So I want to make sure that I have a defined range of motion so that it knows I can't go past here, I can't go past here. And I just like this GIF too.
Yeah, this is cool.
Yeah. Whoever built that is brilliant. So stepper motors. Since some of you guys don't know, I kind of got the feeling last time when I showed my demo that it was not everybody understood. So I wanted to show an example of what's actually going on and the difference between maybe a DC motor or something like that. A stepper motor has, exactly like this GIF, different coils that you toggle on and off, and that actually makes it bump a little bit, and it incrementally goes through different steps. And the basis of the motor is an electromagnet. So if you can think about an electromagnet that, maybe it's a lock on your door and it holds really tight. If you can think about that force pushing and pulling and having a bunch of them push just barely to offset to the next step, so you eventually get this rotation that the GIF, I think, does an excellent job proving. So the basis of this stepper motor is pulsing these different currents across each little nub, if you will, to create a step. And that creates motion. And then you can set the direction based off of which ones you pulse. So you can pulse, back to back like this, or back to back like this, and they change the direction of that step. And in this example, I am using Nema 17s only. I have some Nema 23s, which are larger. The one in this example right here is the Nema 17, very common for 3D printers. So if you have one of those at home, maybe, the Prusa, most of them use the 17. They get the job done just fine. In this case, the upper half of the robot arm has the smaller ones purely for weight reasons. I may change in the future if I found something better. Yeah. So the last part of the stepper, to actually run the thing, you need this motor controller. And the motor controller, you give it a power supply, which is this huge hunk of metal right here. Hopefully, if you want to see, you can come closer to. This is giving off 12 volts directly into the motor controller. And what that does, it allows the microcontroller not to have to carry that load. So that load is only carried by this motor controller. The other thing that it does is it takes pulses and converts them into what needs to drive the stepper motor. So the MCU doesn't need to figure out like how much current and all that, and how to make the actual coils pulse. That's handled in here. The amount of current that's getting driven is handled by this motor controller. So in my microcontroller in Espruino in JavaScript, I'm saying do these pulses, and that is executing those pulses. So what you can see here, I will be posting these notes later so you can kind of see stuff that I'm using. If you want to build that too, it's cool. But I'm using this specific motor driver. There's ones that are way cheaper. I got one for like $2, and that can handle a Nema 17 just fine. So you could probably do this example project for maybe 15, 20 bucks or something. So these are more beefy, they have more current. I'm hoping to carry load with the robotic arm. We'll see. Cool. So this is the code that I put together for running a stepper motor. I'm still lost on how to format the code in the presentation, so bear with me. In Espruino, they copied the JavaScript, Arduino quite closely on the specific method. So digital write, it acts as turning on and off a pin. You set the direction, in this case forward, since it's a 1. And then for a PWM, which is a pulse width modulation, you're sending the pulse to the motor controller in a specific way. And the way that I found works best from JavaScript to run a stepper motor is with the pulse. You could do a digital write, but it really doesn't work well. So what I do is I pulse it on and off at a specific speed, and the speed that I send it is very small, like 1 millisecond, half a millisecond. It's very tiny, the amount of speed that I'm giving it, just a quick on and off. I think we're close to a demo. We'll see.
Is that loop, the digital pulse, or you have that inside the loop?
Yes. So imagine this is inside of a loop.
Okay.
Or it's inside of some control function, and it has a set amount of steps it wants to execute.
Okay.
Each one of those steps executes both of these lines.
Okay.
So it will, one step is both of those lines of code.
Okay.
Yeah, I got a quick question.
Sure.
So I've used this stuff in JavaScript, but writing normal JavaScript and using all this timing functions and all that, the resolution is 1 millisecond. You said you could go below 1 millisecond.
Yep.
And how is that possible?
Physically, I don't know.
Okay.
That's the short answer. In this, I think it tricks it.
And it must be a library, back-end library.
You'll see it. Once I run this, I think it'll make a little more sense.
Okay.
I don't know if it's physically doing that like sub-millisecond execution, but I'm pretty sure that it does.
Okay.
So just based off of how the steps execute. The digital pulse is in the JavaScript runtime, but it's actually referencing the hardware underlying firmware, which is not JavaScript, it's C. So it's executing the set of instructions I say, but it's actually going the next level lower, and it might, I don't know, do you know if Espruino's going binary level or just C?
I think it's just C.
Yeah.
Because it allows you to write C functions as well.
Yeah. So, yeah, it's not actually doing the JavaScript loop.
Yeah, it's not happening in JavaScript. It's happening in the firmware on the board.
The cool part is that I don't have to do that part. So the next thing I want to talk about, I'm using this thing called the AS5048B Sensor. This is something that I showed off last time, which is, I think it doesn't say on here. Okay, so this Hall array is what I kind of mentioned last time, which is basically a bunch of different read sensors, if you know what that is. It's like a tripwire. If you want to set up a security system really basic, you do a wire across 2 points. And somebody trips it and, oh, it's closed. Same idea, just you have a magnet and you've got a switch, just a little tiny wire, and you trip that switch. That tells you that you know it's either on or off based off of the magnet pushing it. In this way, this sensor is actually a bunch of tiny ones in a circle, and then I have a little tiny magnet, which I have, if you want to look at later, you can. There's a little tiny neodymium magnet right there. It's very, very small. And then the chip itself is very small as well. And when you set that magnet above it, it actually can sense the degree, the direction, the angle, if you will, of where that magnet is pointing. And that's how I'm taking reading. And it has a 0.1 degree accuracy from what I found, which is perfect for what I have. It can go lower, but I have found that the averaging of those numbers, it's not much more accurate. So that's what's actually right underneath there, and if you look, the magnet is sitting in there as well. So now we have all the components we need to do a control loop and understand where we are in real space. So, I actually had to write my own I2C library to talk to this thing, which was like, that's why I presented did show until last time, because I learned a lot building a library to read that thing. And to give you sort of a quick snippet, I created it ES6 style. It's just easily callable by the actual sensor name. In Espruino, they have these hardware-defined pins for I2C, and you can call them based off of their global variable names. So you set them up, you tell them which pins they live on. You don't really need to change them. And then I define that connection, if you will, into my module instance. At that point, I can do any sort of angle reading I want to. I can read it whenever I want to. I went up to, I think, 10 milliseconds reading, and that was pretty fast. I probably could go faster, but I was logging all of the readings. So I think the logger at that point was slower than what it could potentially do. I haven't run tests though, so who knows? Yeah, I just want to do a GIF of Dumbledore. Yes.
So that sensor gives you the absolute angular position. It's not like an incremental encoder or anything.
Correct.
Right.
Yeah, I didn't want to go with one of those actually because I wanted to have more free floating and higher amount of accuracy.
Good.
Yeah. Cool. So, first demo, and forgive me if I take a couple seconds here to make sure this runs. But what I wanted to show you is kind of an incremental flow of how I'm learning and building some of these things. What I want to show you is this motor running first, and then I'll show you the reading that's happening, and then I'll show you the full control loop that I've really hacked together that will take the reading and autocorrect itself. So that way you can kind of get a picture of what's going on here. Cool. So, should see this. Yeah. So let me kick it up quite a bit. Let's do that. Cool. Kick it up even more. Oh, I put a limit on it. Huh. So. So yeah, did everybody catch that? Basically, I have the stepper running at half steps, if you know what that is, which means instead of doing full one coil stepping at a time, it's got two coils pushing and pulling against each other, and that gives me a little bit more holding torque. But in this case for the demo, it's got twice as many steps as so I kept incrementing more steps. It had more steps to go.
And Trevor, is that something that you tell the MCU to do? It
Yes.
handles that piece of it, does it?
Yeah, so this little guy takes the instructions and sends those pulses to do each step.
Mm-hmm. But the MCU interprets what's coming off the controller, right? And says, I'm now going to manipulate the coils in this particular way.
So the MCU tells the motor controller to do that.
Yes.
Yeah.
But not in a pedestrian step-by-step way. Does it send it an instruction?
Mm-hmm.
Which is like a mode setup?
It's just sending the pulse on and off.
Uh-huh.
It's not telling it like which coil to do what. It's saying, I just want to go a step and a direction.
But you have do I hear you have a choice in the MCU whether you can set it to do a full step or half step?
No, that's an option. On this controller, it's an actual
I think we
toggle
need to
switch.
define MCU.
Yeah.
Is it a dip switch?
Yeah.
Okay.
It's just on the motor controller. and I can say which amount of, I can do half step, full step, I think there's an 8 step. even.
Oh, okay.
Yeah. So that's handled here. There's other ones that I could software define those, but in this case it's very hardware focused.
Oh, no, it's fine. I was just curious how it was done. That's
Yeah, sorry.
I think you're thinking motor controller and he's thinking microcontroller.
Oh, well, what did you call the motor? Oh, you were calling
Sorry.
it the MCU.
They're very, yeah. So MCU would be the microcontroller in my world. In this one, I'm calling it motor controller. So
Oh, okay.
the motor controller just handles how it's moving the motor and delivering current.
Okay. I got my acronyms mixed up.
That's it. Cool. Yes. Cool. So now I do have a way of reading the position, which I will turn on next. So this one, the concept here is I'm going to turn the motor. I have some math random functions that give it to go away. It just goes and does something. And I want it to turn back exactly where it started from. So we'll see if that actually happens or not. And you kind of saw right at the end it did this. It found that it was off by maybe, I don't know. Well, it'll tell me. It was off by 3.14 degrees, so it moved 20 steps to get back to where it was. In my readings, I'm taking degrees, and then I'm doing some math to figure out how many steps I need to go back, and then I'm executing those steps. And I actually have decided to do that loop twice. I found that in some cases, it got close enough to be 1 degree away after it did that jump, and then I just go back again to double check. In this one, it got back within 1 move, so.
So it only does that twice. It doesn't do it continuously, such that now if you were to push against it with your hand, it would go back automatically.
Exactly. So that's what I'm working towards. In working towards the demo, I've been pretty busy, as you can imagine. Mostly family stuff. But I've been actually focusing on design more than actual code at this point. And I'll talk about that in a little bit. But
Do you find that your repositioning or correction there is affected by precision on the math functions?
not yet.
Not yet.
But I haven't. So I'm still pretty early in the software and testing.
Mhm.
The next thing that I'm going to do is actually have a digital sensor and have a repeatability test,
Mhm.
so that I can calculate what is my, or at least figure out how poorly it operates,
Yeah.
and then tune to that specifically.
I see.
But I'm not there yet. Cool. So a couple of you guys have already asked so far, in terms of the PID controller, like what you were talking about. But I wanted to kind of let you guys know where I'm at, because this is still a work in progress. I'm still in the midst of designing, really. Like, I haven't really focused on driving the motors the way that they should be. So some things I'm working on is the PID controller, which is, again, the positioning. I'm also working on some easing functions so that it doesn't just go full on to a point. I want to actually smooth that out so that it doesn't have some of that jolting. And I also want to have that PID controller knowing where it's at all the time. If I punch it out of the way, it's got to come back to where it was. And then the multi-motor coordination, that's one thing that I was trying to show you guys with the 2 motors going at once. That's super in its infancy. And I want to have it so I can do coordination between 6 motors and then put those motors against kinematics and have this thing do something real. Which, maybe in a few months I'll have that. And the last thing would be button triggers, so I can actually just do demos really quickly with easy buttons. Maybe I'll get fancy Bluetooth controller, I don't know. And the bigger picture goal with this is a full robotic arm that can do JavaScript things, maybe assembly, maybe soldering, maybe 3D printing. That means that it should interpret G-code. It could draw in 2D. The other thing that I have to show you guys after I talk, there's going to be, I have some things that you can look at, some of the parts I've designed that were mock-ups and stuff. I want to create tool heads that are interchangeable. I want to have an actual, I've designed this tool head to be interchangeable, like in a quick way. And then in the actual tool head, I'll have a microcontroller that can specifically function to whatever it's doing. That way you can swap out tool heads based off of the job that they're doing. And then I want to be able to clone that arm and have multiples running together. Some of these are really huge, like pipe dream goals, but I might actually get there. And then bullet points. This is kind of, the last full assembly I did was the outcome here. I was pretty happy with it, except for I tore it apart to take inventory, and there's so many minor detail changes that I made that I have like a whole nother revision that I'm almost done with now. And the one that you see here is that latest revision. It's getting completed in a lot faster than I thought. So, any questions? And feel free to ask me too after we're done. I have other things that you can pick up and stuff. So yeah, any questions?
Do you need help?
I'm glad you